Hello everybody, today we will be going over the introduction to dot product and lines and planes of linear algebra. And this is part of week 3 for 21-41 at Carnegie Mellon University. So let's hop right into it. So today we'll start with scalar multiplication, which we call dot product. And essentially, given two vectors, we iterate through both of them, we multiply each of the iterations, and then we add them together, like so. So with regards to lines and planes, given the line L with the equation 2x plus y equals 0, as I graph it here, we can see that the left side is in the form of the column vector 2, 1, which is the normal vector, which we will call n, and x will be x, y. So as we can see, n dot x will equal to 0 as per our equation 2x plus y. So given that their dot product is 0, we know that these two vectors are perpendicular, hence n is the normal vector. Now we can parameterize this in terms of t and imagine a particle moving along the line. So given xy as per our equation, you can see that xy equals t and negative 2t, which we can take it out. We can take 1 and negative 2 out, which will give us the directional vector, which will be important later. So here is our example. So we have 2x plus y, and we can see that 1, 3 is a solution. It is basically the same line as our initial equation, but we simply shifted it up by 5. Hence, we can see that, n and d should still be normal and directional vectors for this equation because it is simply a vertical transformation. Now, looking at this example, we can tell that the point which we start at is important to getting our normal vector. Hence, we can now write x minus p, where x is our vector, and p is a point, and n is the normal vector. This will give us n dot x equals to n dot p. Hence, the normal form of the equation of a line in vector space R2 would be n dot x minus p equals to 0, or n dot x equals to n dot p, where p is a specific point on L, and note that the normal vector cannot equal to 0. And this gives us the general equation of L. It is ax plus y equals to c, where n equals to ab, the column vector of ab. Right, so moving on. So that was the normal form. What if we want the vector form? Well, we know that x minus p must be parallel or in the same direction as vector d. So in essence, x minus p must be td, where t is simply a scalar and d is a directional vector. Hence, x equals to td plus p, where p is the point. So let's look at an example. So xy column vector and the column vector of 1, 3, where 1, 3 is the point, plus t times the directional vector. And we call this the component-wise equations. And we can easily parameterize this with x equals to 1 plus t and y equals to 3 minus 2t. So hence, the vector form of the equation of a line in R2 and R3 vector spaces is simply x equals to p plus td, where p is a point on L and d does not equal to 0 is the directional vector for the line. So let's look at an example. So this example, we need to find the vector and the parametric equation of the point 1, 2, (-1) that is parallel to the directional vector 5, (-1), and 3. So we know that the general equation is p plus td, so we can substitute it in, where x equals to 1, 2, 3 column vector, and the directional vector times t, which is 5, (-1), 3 in the column. This will give us the parametric equation where x equals to 1 plus 5t, y equals to 2 minus t, and z equals to (-1 plus 3t. Well, and basically, we're assuming that x is the column vector containing x, y, z. So let's look at another example where we're considering the points 6, 1, and 2, and the directional vector 10, (-2, 6. Well, we can basically see that this is just 2 times the original directional vector from the previous example. So we do x equals to p plus td, once again, given the general equation, 6, 1, 2, and then, well, because we know that this is just 2 times the directional vector, we can substitute it. We don't have to use t here. We're going to use s. And now we can so assuming we want to find t in terms of s, we just have to generate the parametric equations for this example, and then we create an equivalency where 6 plus 10s equals to 1 plus 5t, 1 minus 2s equals 2 minus t, 2 plus 6s equals to (-1 plus 3t. So this gives us 6 plus 10s equals to 1 plus 5t, and 2s plus 1 equals to t. So now let's consider another example where we are given 2 points. So p would be (-1, 5, and 0. So p would be (-1, 5, 0, and q would be 2, 1, and 1. And the directional vector, even though I don't write it down, is 3, (-4, and 1. So given the general equation again, x equals to p plus td, we can see that (-1, 5, 0 is basically p, and then we just substitute in the directional vector, and then once again we can write out the parametric equation where x equals to (-1 plus 3t, y equals to 5 minus 4t, and z simply equals to t. So now we will be considering planes in subspace R3. So we know that a line in R2 is represented by ax plus by equals to c. So what about we consider a line in R3? Would ax plus by plus c0 equals to 0 represent a line in R3? Well, no. So as we can see, ax plus by plus cz equal to 0 can be shown as n times x equals to 0, where n, the normal vector, can be parameterized as a, b, c, and x is simply the vector containing x, y, and z. So this is the set of vectors, of all vectors orthogonal to the normal vector, which is a plane. So here is a diagram of us showing that this is a plane, not a line. So as we can see, the arrows represent all of the vectors orthogonal to the normal vector, which is represented by a red line. So what does this imply? So to find a plane in R3, we simply choose a random point on the plane and a non-zero normal vector to P, to a point. Thus, X represents an arbitrary point on P. So, well, we can see that the equation of this is basically the same as a line where n dot x is equal to n dot p, where simply we just do n equals to abc and x equals to xyz, simply with more variables, more components. So that is basically the normal form of a plane in, well, vector space R3. Yeah, we simply just have different components. So let's use an example here. I'm writing these in so you guys will have the notes later on. So let's assume that we have the point 6, 0, and 1 in the normal vector of 1, 2, 3. So this will give us, so let's consider the general equation of n dot x equals to n dot p. So we know that n dot x just gives us the equation x plus 2y equals to 3z, and n dot p gives us 1, 2, 3 dot 6, 0, and 1, which will give us 6 plus 3, which will equal to 9. So, yeah. So now we'll be thinking about, well, we express lines in vector and parametric form. So how do we express a plane in vector and parametric form? So, well, first we have to consider how can a plane be determined? So determine a plane. So what we need is two directional vectors, u and v, that are not parallel to each other, but they are in fact parallel to the plane. So right now I'll draw an illustration of what we are looking at. So this is a plane, and we have a point on P, and we have the vector v, directional vectors v and u, and we have another point, x. Then we can see that x minus p equals to su plus tv, which will give us x equals to p plus su plus tv. Well, we also got to remember that u and v are directional vectors. So hence, the vector form of a plane P in R3 is x equals to p plus su plus tv, where p is a point on P and u and v are directional vectors. So let's look at a vector from, well, let's look at an example. So we consider the vector form of P equals to 6, 0, 1, n equals to 1, 2, 3. So let me show you my initial way of approaching this. So I thought that the P would be a column vector, and then we wanted to find two parallel vectors, but as we will see, this way doesn't really work out. So what we're going to do now is the way that we're supposed to do it, which is the better way, where we identify that we have to use the general equation, where n dot x equals to n dot p, which gives us our initial equation, which is the equation of the plane. So then we gotta think, what parameters, what x, y, and z would fulfill this requirement? So initially I thought 0, 0, 3 would work, 1, 1, 2 would also work, but as you'll see, the textbook uses different numbers as components. So even though the numbers I give, 0, 0, 3 and 1, 1, 2 in P, they both work, well, we're going to stick to the textbooks. 6, 0, 6, and then that's the point as given above, and then negative 6, 0, 2, and then negative 5, 1, 1 t. Sorry, I'm taking a while to write these down. And that's it. So some final remarks on this subject matter is that we learned that a plane is simply a two-dimensional object. And because it is a two-dimensional object, its equation in both vector and parametric form requires two parameters. And also, given a point and a normal vector n, there are infinitely many orthogonal vectors to n. However, I do not write this in the notes, but however, given a point and two non-parallel normal vectors, we will be able to identify a unique line. But that is not important. Well, it is, but you won't need to know that in the notes. So another thing that is important to know is that the intersection of 2 points also forms a line. And here I will draw a diagram as such. So that is one plane, and this is another plane. And as you can see, when these two planes intersect,